Hello. This week, the lab is focusing on phasor-domain analysis techniques, which are essential for solving linear AC circuits in the frequency domain. By transforming sinusoidal light signals into phasors, this allows the application of algebraic methods to simplify the circuit analysis. The learning process is a standard structured in three steps: analysis, simulation, and measurement, ensuring comprehensive understanding of both theoretical concepts and practical applications. Using multi-sim simulation toolkit, we will virtually construct an AC circuit, apply phasor-domain principles to verify theoretical predictions, and this hands-on approach enhances the design, analysis, and interpret circuit behavior effectively. Additionally, we will utilize the analog discovery 3, which bridges the gap between theoretical understanding and real-world circuit behavior. Primary objectives will be constructing an AC circuit in both simulation and hardware environment and practicing voltage measurement techniques using multi-sim and analog discovery 3. Utilizing the phasor domain analysis techniques of Chapter 7 AC analysis in NI MIDAC multi-sim, we create a circuit as shown in in this monitor right here. Over here in multi-sim, we have a voltage source with 4 volts peak, 1 kHz at 0 degrees. The second voltage source, we have a 2.828 voltage peak, 1 kilohertz, and minus 90 degrees in phase. C1 is a 0.047 microfarads. C2 will be a 0.1 microfarads. We'll have R1 at 1.5 k ohms, R2 at 2.2 k ohms, and R3 at 4.7 k ohms. We've hooked up the oscilloscope at VA, which is between R1, R2, and C1, and then the second channel between R2, R3, and C2. And then both of the negatives of the oscilloscope are connected to the ground down here. Next, we'll go into simulate. We'll go in analysis simulation. We do an AC sweep, starting at 1 hertz, ending at 2 kilohertz, linear with 200 points, and we go and run that. We get an AC sweep that looks as follows. We have our 4 volts over at the input of the voltage source 1, and the 2.828 right here, this green line right here. Then we have VA, and it's decreasing through here, and VB, and it's decreasing through there. Same thing with its degrees. We have 0 degrees for the voltage source 1, minus 90 degrees for voltage source 2, and we can see a decreasing in degrees as we get further away. We go to cursor, and we go to select show cursor, and we're going to show both cursors. I'll show cursor 1 for right now. And then we'll go to X value and set that to 1000 hertz. We end up having a voltage at VA of 2.372 and VC or VB at 1.5932. Next, we're going to go over here and go to simulate again, but this time we're going to do interactive simulation. Save and then run. Our oscilloscope comes out over here. We got all these lovely wobblies. Stop. We'll then go ahead and reverse this till we can get the beginning point of both waves on the screen. So our beginning point for channel 1 is here and channel 2 is here. We'll then take our time domains, and this one is 2, so this won't go down here. We'll get this as close on channel B 0 is possible. I think that's going to be right there is going to be close as possible. That's going to get take this one over here and get it as close as possible in channel A on T1, and I think this one's as close as possible. Then we have our T2 minus T1 is at 1.78 milliseconds between these two. But what we're going to need to look at actually is we're going to now connect B over to this one, which is at 0, so we can actually see what the true difference of the two would be. Once again, we'll take T2, put it as close to 0 there, T1 close to 0 on channel B. So let's see, channel A or channel B, hold on. Yeah, that's about as close as we're gonna get. And we have a 0.8417132 microseconds between the two. So that is our multi-sim measurements. With the problem checked out in multi-sim, next we're going to hook up our breadboard. We have our channel 1, or our waveform 1 coming in right here as to this power bus here, supplying all the power off this side. Then down here at the bottom, we have our waveform 2 coming in here. Next, we'll look at our components. We'll connect waveform 1 to the top part of R1. R1 will then come down here and connect to R2 and this capacitor right here, C1. These two will come down, and then R2 will connect to R3, and then this capacitor right here, which is C2. Both C1 and C2 are then connected on the other ends to ground. And then R3 is connected to the waveform 2 right here. Next, we'll look at our grounds. My ground would be right, this is the ground for the bus right here, which supplies this whole entire bar right here, all the way down here, which we also are putting channel 1 and channel 2 of our waveform reader for our analog discovery 3 into grounds over here. And then our connectors for in here, oh, this is also the ground for C2 is this one right here. Then our two positive pins for the oscilloscope are here and here for right now. We'll move those along as we go. Now looking at our waveforms, we're setting up our first waveform. It's going to have 1 kilohertz, period of 1 millisecond, and amplitude of full volts, and our phase of 0. And then the second sine wave will also at 1 kilohertz. This one's at an amplitude of 2.82 and a phase symmetry of 2.70. Further all up here at this part, we're going to click this into synchronize so these two go in the proper way. Next, at our scope, we're set at a time division of 200 microseconds. Channel 1 is at 1 volt, channel 2 is at 2 volts, and then for our measurements we have our amplitude here and here for C1 and C2, and our frequencies both at 1000 when we go to run. And then go ahead and make sure our buffer is at 100, just because I like it there. Next we start both wave gens up and then the scope up. We get our nice little wave right here. Go ahead and stop both now that we have our waveform up here. We can now check our voltages at 2.3531 and our amplitude at 1.6303. If we go into our multisim, we can also see that our voltages for Vmax we go back to the simulation of an AC sweep, and we run that again. We'll see our voltages for VA was 2.3372, back over at our waveform, 2.353, well within the margin of error. And this one is 1.603. We'll go back to it here. This one's at 1.5938, pretty close. Finally, if we go into our MATLAB and connect this to our calculations, finally comparing this to our MATLAB, we had VA of 2.3377 and phase angle of negative 30.20 degrees. And VB we had at 1.5925 magnitude and a degree angle of negative 94.29 degrees. Finally, comparing these to our Excels, in Excel, VA, MATLAB we had 2.337, multisim 2.3372, and waveforms 2.3526. Percent error between all these is about 0.65%. As for VB, we go from 1.5925, 1.5938, 1.6303. We have about 2.37 between waveforms and MATLAB and a 2.29 between waveforms and multisim, for an average of about 2.33% per average error amount. All right, thanks for watching.